there's a big vacuum at the time, which is my attempt to solve the superconductivity problem, which I failed to do. Let's talk about Feynman and the time that he missed. Now, its story doesn't really have a lot to do with Feynman right away. It's kind of an interesting story that my advisor was telling me about when we were doing our advanced condensed matter class. Let me list you the main paper that I kind of looked at to get all of this information from. And then you're welcome to use that. That's my resource. It's written by two people out of Caltech, David Goodstein and Judith Goodstein. David is a professor of physics at Caltech, and Judith Goodstein is a professor of history and university archivist, like archive, at Caltech as well. So they are people who have experience or interacted with Feynman. Some of these stories are from them, like interacting with Feynman, and some of these stories are from the archive. So, here we go. Let's talk about the time that Feynman missed. Does anybody know the story off the top of your head of the time that Feynman was not, when he lost a contest? He lost the contest to find something first, and he was not able to succeed. Does anybody know that story? Stove says nope. Interesting. It's not, I didn't know either. I didn't even know he thought about this until at the end when they explain why, the weird country thing. You mean GeoGuessr? No, I don't know if Feynman played GeoGuessr, but, maybe. I do not recall. I read some Feynman. So Feynman actually attempted to solve the problem of superconductivity and fell short. Maybe by only a short period of time, but ultimately it was one of the times where he felt super defeated, which was an interesting thing. And by the way, Feynman's birthday was yesterday, so we are celebrating his birthday by talking about the time that he missed. But let's talk a little bit about the history of superconductivity and then the role that Feynman actually played in the very end of kind of figuring out low temperature superconductivity, which there's a big difference between low temperature superconductivity and high temperature superconductivity. And it starts with two experiments that kind of show the effects of superconductivity. It starts way before then. Like even a century before then is when people started to realize that weird things were going on at low temperatures in some metals. And but the two experiments that I'm talking about is one in 1911 by Onus from the Netherlands and one in 1934 by Meissner and Oxenfeld, which I think was German, but these were both experimental, two very different things. One, we're going to talk about Onus a lot more in the beginning, and he was actually racing another scientist, a British scientist named Dewar, I think Sir James Dewar, to try to liquefy helium, or hydrogen, excuse me. Hi, Peps, good to see you. They were trying to race to liquefy hydrogen. And Dewar actually, the British scientist or physicist at the Royal Institute, was able to liquefy the hydrogen first, but Onnes kind of like Onnes, if anyone's looking that up. But he kind of gave up on the hydrogen at the very end because they found terrestrial or on Earth, for those for us who are challenged with words like myself, helium. And then the question began and the race began, can you liquefy helium? Which this was from 1911. This was before 1911. This was like 1905, 06, kind of like when Einstein was coming onto the scene. And they didn't even know helium was on Earth until they found it. It turned out that the States had a lot of helium. But again, unaware at the time. Anyways, but then, so he did find that you could liquefy helium, and then there were some interesting effects of that liquefying helium. Basically, there was a bunch of subsequent events leading up to figuring out that the resistivity of certain gases or certain metals, resistance in those metals was zero. But this led a huge problem. And what happened is, I guess I can show you the problem in a video that we did on stream not long ago, over the winter sometime. So let me see if I can bring that up here. Calm down. You calm down. And here we go. Let's see. Oops. Now I can't see because I have my notes up. Oh, we're there. Okay, cool. And balloons were invented right after. Okay, that might be true. I have no idea the history of balloons. But nevertheless, we're talking about superconductors. So look at this. This was the Meissner effect, which eventually was solved by Meissner after the 1933 experiment. Was it 1933 experiment? Hold on, I need my notes again. The 1934 experiment by Meissner and Ockensfeld. And what... This was also noticed in the earlier events leading up to this, but let's take a look and see what happens if you supercool one of these superconducting materials. Okay, let's take a look. Let me make this full screen. Let me go away. Actually, I can probably stay here, and then let's play it. In those statistics, ooh, look at that. It's not cold enough now. Let's see if it will do it on its own. I don't know if it will levitate on its own. Levitate? What do you mean levitate? Once it gets cold enough. So this thing, hold on. So this thing that I put on top here is a magnet. So I have in this little container, I have this superconducting piece of material and then this magnet that's put on top. Okay? Let me know if anybody was here for this experiment. We did this live. But anyways, so you guys will see. Oh, look at it go. No way. So what's going on here is this was an event that was found, or this was found kind of later on. That what's going on here is that the wait, where's a good one? I want to do that one. Didn't I do it earlier than that? No, really? Come on. I started with the little square. There we go. So what's going on here is that what they thought was happening was that there was surface eddy currents happening, right? Definitely so drunk cool. At the time. Okay, so would you be quiet, Eric? So what's going on here is they thought that there was these surface currents that were coming up from this supercooling liquid, right? They thought that there was these surface currents coming up, and that must have just be doing some eddy currents in it, so that when you put this magnet nearby, the resistivity was so low in these materials. That's what they originally found, that the resistivity or the resistance was so low in these materials that if you put a magnet nearby, you would get an induced eddy currents in the surface. These induced eddy currents would make just the right amount of magnetic field that would repel this magnet perfectly, so that no magnetic field would go through this material. There were some problems with this thinking, and they kind of knew that at the time. But this was a good enough explanation that they kind of went with it. But this was really what was thought out. The problem is, every time they wanted to connect this, where are my notes? This phenomenon with theoretical data, they got weird things. They could not relate the quantum mechanics that was showing up in like the 1920s. Of course, when those were first discovered in 1911, they just assumed, no quantum effects at all, because quantum wasn't even that much of a thing. I mean, Einstein just talked about the quanta of a light, the wave-particle duality, in 1909. So now 2 years later, when people are still like, I don't know about you, dude, then they were, then he was saying crazy. Then people were talking about that he was saying things like, okay, well, this must just be something simple. We can explain it with, eddy currents and low resistance in the material. And that was just how they chose to explain it at the time. But then they tried to introduce in the 1920s this concept of, of quantum mechanics and how could it be evolved at a microscopic level. There is one third experiment we should talk about, and that was in 1986. The IBM laboratories found high temperature superconducting, I think in like the 50s and 60s, maybe 70s even. I bet you I could just look it up. Ducting temperatures. We're up to 59 degrees Fahrenheit. Sulfur compound. It's the milestone was the hydrogen carbon sulfur compound, and was reported on October 14th in 2020 in Nature. Yikes. That one is what's YBCO? Transitions at 70 Kelvin. But this is 59 degrees Fahrenheit. That's high. That's very high. That's like 60 Kelvin. 59 Fahrenheit. to Kelvin. 287. Oh, wow. Really? That's a lot higher than I thought it was. I thought 273 was room temperature. 58 degrees Fahrenheit's not room temperature? What? Anyways, 287 Kelvin. I think that one is under intense pressure. Is it? Either way, they found high temperature. In 1986, they found their first high temperature superconducting. We're not going to talk about it anyways, but it's just an interesting thing to talk about, I guess, in general. Very cool. But anyways, so Onus, again, he was trying to attempt to liquefy hydrogen. He was racing Dewar, and ultimately in 1911, he was able to liquefy the hydrogen. And then he noticed that the resistance of that material was going very, very, very low. And they show graphs in this. Let me see if I can show you the graphs in this of when they figured out in other materials using the same apparatus that they used to liquefy helium. Did I switch? No. Okay, yeah. You can see the graph as it's like, the resistance plot. So Onus's graph plotting electrical resistance of a mercury sample versus temperature in kelvins. So the temperature in kelvins is getting down closer and closer to 4 degrees Kelvin. This resistance just plummets to 10 to the minus 6. So this was the cool thing that we're finding out in these materials. So I guess he was using mercury in this situation. But Onus was the one that figured out first, and then so let's talk a little bit about what happened after Onus. So then research actually stopped shortly after that, right? Let's go back to here. Research stopped shortly after that because World War I. There was obviously the World War I stopped a lot of research between the different fields, between the different countries, excuse me. And this was a widely celebrated thing that everybody was doing. That's one of the nice things about physics is it was bringing a lot of different countries together. You had people, and it was competitive, but it was, it was still good that everybody was working, at least working competitively, but together to get these things done. So research stopped in World War I, and it began again in 1919, and I guess Onus and a couple other groups just found a bunch of superconductors after that. I guess there was big caches of helium found in the States, and they started shipping it to Europe, and the European scientists were finding superconductors left and right with all the materials that they were finding, which is cool. But then again, there was this 1922 to 1933 time frame where quantum mechanics were really the new kid on the block. Everybody's excited about quantum mechanics, wanting to learn more about the very, very small microscopic things. And this had a lot of big people who were trying to take this effect of having the resistance of a material go to zero and now try to talk about it microscopically, right? Especially because, right now, we're still kind of believing that the idea is that there's just these eddy currents that show up because of zero resistance, and Lenz's law, blah, 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 that whole thing going on. Well, there's big names on it like Heisenberg, Landau, Pauli. These were the people who were working on it. And there's more too. This article lists a bunch of people who were working on it during this time, and everybody was just kind of beating their head against a wall. And then finally somebody, I think his name was Max van Laue, proposed to Meissner to see if he could get the eddy currents to a type of experiment that was to see if he could get the eddy currents to just show up on the surface, or if he could find them in the bulk of the material. So Meissner, he recruited he recruited Oxenfeld, yeah, and then they were able to show that it was happening, that it wasn't in this current, that it was or in the surface, it was happening in the bulk of the material, and there were some weird things happening, ultimately what they showed was that video that we were talking about, where these mysterious currents inside this material were able to produce a magnetic field that exactly matched any magnetic field that got close to it, and would subsequently, repel the magnetic field, so you could get this levitating effect type of deal. So now we went from having this. That's extremely hard. Yeah. So they went from having this material that could be completely resistance-free to now having a material that is a perfect diamagnetic, where it will just have a magnetic field that will match and cancel out another magnetic field. And so these things were very confusing and not well understood. Well, unfortunately, shortly after that stuff, we went to war again, World War II. So everything was stopped again in the research in the research for trying to figure out how to connect quantum mechanics with the Meissner effect and the drop in resistance. In my magneto-optical trap, the trap would get messed up by a single car parked in the lot outside my window. Holy smokes. That's wild, Admiral. That is wild. Yeah, that's absolutely insane. Yeah, I mean, magnets are crazy. We've talked a lot about magnets are scary to some degree. They're powerful and nutty things. But this wasn't magnet stuff. This was like, so I guess there was some other problems. The paper's really good. The paper that I linked earlier, David Goodstein and Judith Goodstein, they list so much like cool history of everything. Like Onus had his lab shut down. Because of how low the temperatures were in the early 1900s, he had his lab shut down by the town. They wouldn't let him experiment anymore because of the liquid hydrogen that was underground. Dewar almost had the same thing happen to him because he was working with liquid nitrogen underneath the Royal Institute lecture. You could just go to the Royal Institute YouTube channel. Let's do it. You just go to the Royal Institute YouTube channel. Royal Institute. Let's see if we can go to the YouTube channel. Okay, so that's not. There we go. No, wait, Colombo. YouTube. Okay, there we go. And you can just look at any of these lectures happening in the lecture. David Tongs is a good one. In the lecture auditorium, right? I think this is the same lecture auditorium. I'm almost 100% sure. And directly below this, you have Dewar. Sir, I think his name is James Dewar. I think Sir James Dewar, something like that. Working with liquid hydrogen, this incredibly explosive substance right below that. And people were like, well, this is a really bad idea. Hi, Parzival. Good to see you. Welcome in. Well, anyway, so they let him continue on, but the people in where Onus lived, in Onus's laboratory in the Netherlands, they shut him down. And he had to put in a ton of safety precautions before they let that happen again. I believe it's also where Faraday, yes, it is. Yes, it is where Faraday held his public Christmas lectures. It was wild. It's just dripping in history. It really is. And yeah, so it's just crazy to know that underneath this, this lecture auditorium was, Duares like in a mad race to be the first person to liquefy hydrogen. So then, so where were we at? We were talking about, okay, so after World War II, around 1950, research on superconductivity began again. This time, it was completely different. The research in 1950s was fast and wild. Like they make it sound like it was this like long, drawn out thing, but like it happened quickly. By 1957, it was all done. But in 1950s was where things started to get interesting because Bill Bardeen, who was known for his work on the transistor. Bill Bardeen ended up winning a Nobel Prize for the transistor. He turned his attention onto the superconductivity and thought, hey, maybe I can make this happen using what I know about solid state physics. And let me see if I can find some of the more details of how they actually did it. I guess we'll get into it in a little bit. Is it John Bardeen? I thought it was Bill Bardeen. No, it's John Bardeen. Excuse me. John Bardeen. And he turns his attention in 1951 to this problem, and he there's rumors that University of Illinois at Urbana Champaign, something like that. What's the C? University of Urbana is what Illinois. University of Illinois at Urbana. There we go. What's the C? I think it's Champlain or something like that. Urbana Champaign. Champaign Urbana. Okay, cool. So John Bardeen is there and he's working on it. There's rumors that Feynman has taken on the problem. But like nobody's heard anything from him. Nobody's seen him talking about it. He won't talk about it publicly. He's not publishing papers. There's just rumors that he's working on it. So John Bardeen, I guess this is like, the 50s. Things are really, really, bouncing off the walls right now. I mean, 1949, that was when Freeman Dyson literally just united Feynman and Schwinger's work together. And QED was like, the nail in the coffin on QED. So like there's this super in-depth understanding of how to do quantum electrodynamics. Everybody knew that this problem had to do with electrons, but nobody really knew like how to handle it. And everyone just assumed it was some sort of scattering process inside the bulk of a material. So Bardeen was nervous that now that Feynman was working on it, he was going to get it. So he goes to C.N. Yang, and he says to C.N. Yang, I need some help. C.N. Yang was one we talked about recently. Would it be an exaggeration to say that no other invention in the last 100 years has had a wide impact as a transistor? I don't think so. The transistor is pretty wild. I don't know, like, all I know about the transistor is from what everyone else has told me, and it was certainly like one of the biggest, that's everything that we use nowadays uses transistors. Like every type of electronic, every type of computer, everything is built off of transistors. So Bardeen was certainly, found it in a Mini Cooper. What? Bardeen was certainly well known for this discovery, and so he goes to C.N. Yang and he says to C.N. Yang, "I need some help." And C.N. Yang recommends Leon Cooper. Not so much of a Mini Cooper, but Leon Cooper. And Bardeen also has a graduate student, Schreifer, and notice the initials. Bardeen, Cooper, and Schreifer, and they start working on this problem. Well, in 1956, Cooper has the revelation of what later becomes known as Cooper pairs, which is that in certain situations, two fermions can basically act as a single boson. But those conditions are, that was what people were trying to figure out. And really this working with Cooper, I guess the authors do a great job explaining that it had its up and downs. There was some, Bardeen had to convince Schreifer to stay on board because Bardeen was going to get his Nobel Prize for the transistor, and Schreifer was done and wanted to leave. So Bardeen is like, please don't go. Stay on while I go and get my Nobel Prize, and when I come back, we'll finish up the project, and then you can go. So Schreiber agreed to it, kind of like they've been hitting their heads against this wall for 7 years now. This is 1957, but finally, at 1956, Cooper drops the Cooper pairs research, and they ultimately are able to figure out that one of the conditions that results in a Cooper pair, and one of the effects from that Cooper pair, is this diamagnetic effect inside of this material at a certain temperature where superconductivity takes hold. So, there was, that Cooper and Bardeen had to share an office, which was really cramped. Schreifer was working in like a, what's it called? Where you have like the, the pen or whatever, where it's like a huge room. Yeah, so there's like a huge pen of graduate students just researching, and Schreifer was amongst them. But they managed to figure out what's going on. We'll talk a little bit about the physics in a second. I think I'm going to need to use the paper to kind of help me through some of it because it's a little bit complicated. But the idea is that fermions under a certain temperature will group together and act as a boson. This boson will then, they will reject any type of field that comes through them, or any type of magnetic field that tries to go through them. So that's how they were just rejecting the magnetic field, by making these little currents that would match whatever magnetic field was showing up. But again, I don't know of the 100% of the really rigorous stuff behind it, unfortunately. But anyways, beyond that, let's sort of figure out how this has anything to do with Feynman, okay? All I said so far was that Bardeen had caught wind that Feynman had been interested in the project. So now Feynman was asked by a group of people to give a lecture in the middle of the 1950s. It turned out it was 1956. 1956, after Cooper, I think it was after the Cooper pairs, but before BCS had released their theory on the BCS theory. Because that was in 1957. April 1957. There we go. So Feynman says during that interview, so he's in an interview, and someone asks him, what were you doing in the middle of the 1950s? And Feynman says, oh, during that period, I spent an awful lot of time trying to understand superconductivity. There it is. So now it's in his words. I did an awful lot of calculations and developed a lot of methods, which I've seen gradually developed by other people for other problems. But I didn't solve the original problem that I was trying to solve, which was, where does superconductivity come from? And so I never published anything. But I have done an enormous amount of work on it. There's a big vacuum at the time, which is my attempt to solve the superconductivity problem, which I failed to do. There it is. Feynman admits he missed. He missed on this one. The interviewer asks, but you did publish an article on superconductivity and superfluidity. And Feynman says that was probably the result of some meeting where somebody asked me to give a summary of the situation or something. And they did. That was exactly it. Somebody asked him to give a summary on the situation. He wrote down some stuff. And guess who put all of that stuff together in a periodical? Guess who had to take Feynman's remarks on superfluidity and superconductivity and prepare it for the journal? It was, in fact, Schrieffer. Schrieffer had to put all of Feynman's remarks together. Meanwhile, Schrieffer had known that they were very close or have already completed solving this problem. So that was really, really funny. Really funny to me to hear that little bit that, like, Schrieffer is amongst the graduate students forced to combine all of Feynman's notes, and those notes are how hard superfluidity and superconductivity is, which I thought was really cool. But yeah, so it was really interesting. Let's see what else Feynman has to say. It says quantum mechanics was developed in 1926, and in the following decade, it was rapidly applied to all kinds of phenomena. With an enormous qualitative success, the theories of metals and other solids, liquids, chemistry came out very well, but we continued to advance the frontiers of knowledge. We left behind two cities under siege, which were completely surrounded by knowledge through themselves and remained isolated and unsaleable. Schrieffer killed the guy? He wasn't the guy who drove really fast on the highway, was he? The one that ended up going to jail for a long time. Was that Schrieffer? It was him. He ended up going to jail for like a long time, didn't he? Or like, is he still in jail? That's a story all in itself. Holy smokes. But he was driving very recklessly and killed a guy. I didn't know that was him. I remember that story, but I didn't know it was him from BCS Theory. That's insane. That's utterly insane. But anyways, let's go back to the story a little bit. I was kind of hoping to kind of dig into this a little bit to talk about where he went wrong. But I guess I can maybe just summarize, and if you want to read it, then this is the article to read. Basically, he goes into a long thing from the Feynman lectures, which I didn't really understand too much as far as the relevance of it, But yeah, so I guess the thing is like, so Feynman wanted to solve this problem by I was hoping to find it here. Basically by using what he did with QED. Like, he wanted to find the diagrams that explained it. He wanted to find the physics that, he wanted to do the QED that he had developed, and get this, figure out what was going on with the resistance, figure out what was going on with these fermions, these electrons, and figure out how they behaved. Whereas Bardeen and Cooper, they did have an imagination. I'm going to read that that last problem, or that last sentence from that paragraph in a second. But it was just, what they did was they just, there we go. We know in retrospect, this is again the authors, the reason why Feynman failed. It's because the correct BCS solution, the energy gap, is related to the electron-phonon interaction strength by an essential singularity, a mathematical form that cannot be expanded into a power series. Therefore, it cannot be derived by perturbation theory. And that's what Feynman was trying to do. He was trying to use the perturbation theory of QED to get this interaction, but instead it's related to an electron-phonon interaction, and that is a singularity, something that Bardeen, Cooper, and Schrieffer were able to figure out. Okay, so this is what we're going to end on. This is really fun. So still, so this is what it says. So still at that, who tried hard and did not fail. So still at the poignant moment, just before the citadel of superconductivity was to fall into other hands, Feynman knew the time was ripe. Why haven't we theoretical physicists solved this problem yet, he asked. We have no excuse that there are not enough experiments. We should not have to look at the experiments. Every time we look at another experiment, it makes the problem easier. It is like looking into the back of the book for the answer. He concludes the paper, this is his remarks on why this is still a problem. He concludes the paper with the remark, the only reason that we cannot do this problem of superconductivity is that we haven't gotten enough imagination. And then the author says, as it turns out, Didnt, Cooper, and Schrieffer did have enough imagination. That's cool to hear that they were able to figure it out. It's wild to think that like the problem was in, a solid state physics solution where you just had to take a look at the energy gap. You had to figure out that it was a singularity that could be solved through the electron-phonon interaction. And that's ultimately what Didnt, Cooper, and Schrieffer were able to do, and why Feynman why Feynman did miss. But it was a very cool story, very interesting story. Now we know it very well. But we are finding out some different things. There's another anecdote in the end from one of the authors about Feynman made a prediction that strontium or scandium would be the highest temperature superconductor that they would find. But turns out there's only one element that no one has ever been able to make into a superconductor, and it is scandium. So either Feynman hit the nail on the head with scandium saying that it will become, it will be the high temperature superconductor, or is just another miss. Superconductors were always the thing that slipped through Feynman's fingers. Very, very good, very fun. I like that story. Apparently some people said he got really angry. I never had anything to believe that he got very angry. SSTA, thank you for the follow. Welcome. Yeah, so I hope you like that story. Superconductivity. A wild story, a lot of drama going on in that about who's getting to where first, who solved what first, and then ultimately Didnt